different areas, mainly to find out what are the grand challenges and what we need on instrumentation to solve that. So Manuel was nice enough to organize this workshop on 2D materials and synchrotron radiation. And let me go you a little bit walk through the different kind of background information. So first of all, as you may know, ALBA is now nearly 10 years operational, and we have a very productive user program. And over the years, you can see that the program itself has focused a lot on health, energy, and information technology. And our mission really of ALBA is really twofold. On one hand, we have to support obviously all Spanish and all international users. But on the other hand, we want also to have some kind of leadership and specifically support some focus areas. So these 3 areas, what I said before. And for that, we tried to push really what we can do on synchrotron characterization for getting information on electronic states and on the structure of the material, and also to understand how these changes of these 2 things are correlating the function of the material. So that's one thing. The other thing is that we tried to have additional characterization tools to push into the atomic and subatomic resolution. And here's obviously the usual suspects like TM and also STM. And then we have also recognized that with this kind of increased problems, what we want to study, we need really to have a much better organization in additional support for sample growth and for also computation. So that's another focal area where we want to grow. And the last thing is really because of the complexity and because of the microscopy, you have to really broaden the view from a single experiment to a multimodal approach. And so we try to get to methodologies which are using this multimodal approach. So now more to the ALBA II. So the upgrade decision for ALBA II was taken by the funding agencies in December 21. So this was a very fast process. And the goal of this upgrade are fourfold. So number one, we want to bring all the systems what we have in ALBA to a state of the art so that they can operate highly productive up to about 20-25 years. Sorry. We will significantly strengthen the microscopy sector, which is an obvious thing when you go to the 4th generation. But we want also to provide high throughput capabilities and integrating from the beginning on the big data approach in this research portfolio. And this is obviously mainly in these 3 main areas. And then strengthening the operando and in situ capabilities. If you think now on the timelines, so we are forced really to be very, very fast. And so we have to be very efficient in communicating. And that's also why these workshops are so important. So the idea is that we have a first additional beamline decision done in January 2022. The accelerator complex and the instrumentation, a first preliminary design of that should be available in the mid of 2022. And then the operation should go up with about to 28. With a shutdown in 29 and 2030, the synchrotron should come back. Now this last point is very speculative and it may be much faster, not likely that it's shorter. So we have some kind of wiggle room here, and it depends really on the money flow and where the money comes, what kind of timeline we will get. Here's a short picture about what ALBA II will be. So it's a typical fourth generation source. The ID lines are pretty much where they are now. They move a little bit, but not much. The bending magnet lines will most likely move, and we will get 8 of them with super bands. And there will be 13 ID lines. And from the 13 ID lines, we will have 4, which are either long or can be built long or medium lengths. So this gives obviously a bunch of new opportunities for really extreme kind of experiments. And we will decide in principle the last available beamline in this kind of round now, where the decision has to be made in January. So this workshop is really important to nail down if we have a need of specific instrumentation in this field. Now, to show you a little bit the context in which the workshop or the workshop program is in comparison to everything else, what happens. So we have here in the middle, you see the workshops, and there's also a colloquium if you have not already seen it. And then we have on the one side, the section reviews, and I will say later about that. And we have a call for new instruments, which will come out at the end of this month. So let's go to the workshop program. So the goal here is to identify the grand challenges in the different areas where we are working. The second part is identify the needs, the characterization needs, or also the kind of sample preparation needs. So any kind of resources, what you need to make a successful experiment. And then we want also to create in the community awareness about this process so that people get really organized and can actively participate. For the stakeholders, we have the Spanish community, obviously. We have the international community, and there are the ALBA employees, and very important, ALSE, as the representative of all the user communities. So all these people should play a major role, and we invite everybody really to participate and work with us on defining the science case, but also the kind of plans how we can upgrade. The call will come out, as I said already, relative soon. The idea is obvious, so we want to have the identification of the different instruments, and we want to group also the people around the instruments so that we have strong teams which will push for these instruments and then also get it further. So here again, the Spanish community, ALBA employees, but also international community is welcome to contribute. So, but it's important that there's always a Spanish community involved. And for the section reviews, only very short. So the goal is the mission verification here, the strategy review, the gap analysis, and the review of all the services, what we are at the moment providing. And then stakeholders here, experts, national user community representatives, and a sector expert. So all that together will form our scientific program, and then also will impact dramatically what we do with our preliminary design. So it's really important to participate here. And here a little bit of timeline. You see in this part here, we have the workshop program. So you see that we are with this workshop ahead of our timeline. So this is very nice. But it will go on in principle the whole year, and we will have multiple workshops to different areas. The call will open in April. There will be a first feedback in June. And here we will only collect really the rough information, and then we will go out and invite the full proposals, and this has some time between June and September. And then in October, November, there will be the review by an external committee. And in December, there will be a first version of the science case and the white paper. And finally, in January, there will be the SAC review with the suggestion what instruments will be built. And the reviews will take place between May and July. Yesterday, a discussion about the electronic materials and device review. So that's really mainly the magnetism part. And that's pretty much all that what I have to tell. So if there are any questions, please let me know. And otherwise, I wish you a lot of fun with the workshop and enjoy the different talks. Thank you very much.
Good morning, everyone. So we'll start with the first session. The chairman will be Sergio Valenzuela from ICN2. And remember that there will be different sessions and break, and the different sessions will have different links. So good morning, Sergio.
Good morning, everyone. Thank you for the introduction. Also, it's a pleasure to be here and act as a chairman. It's a very nice workshop, mini workshop. Here in the first session, we will have 4 invited speakers. We'll give 25-minute talks. We have of the order of 100 attendees between panelists and conventional attendees. So the way we are going to have the question and answer session is through this little icon that you will find at the bottom of your screen. It says Q&A. So you type in your question, and then I will read it to the speaker. This will be the most efficient way, and then you have the answer there. So the first speaker of the session is Andrés Castellanos, who is a CSIC researcher at the Institute of Material Science in Madrid. And he's going to talk about the strain engineering in 2D materials. So Andrés, floor is yours. I'll disappear now.
Thank you, Sergio, and thank you, Manuel, for the invitation to the workshop. It's a pleasure to be here and opening the session. So indeed, I'm going to talk about two-dimensional materials and straintronics. I hope that you can see now the slides. It's okay? Okay. All right. So I indeed moved to the Material Science Institute of Madrid, that is part of the CSIC, in March 2017, and there I became part of the 2D Foundry group. It's a research group that basically gathers different PIs with complementary interest in two-dimensional materials. So we basically are all interested in two-dimensional materials, but we tackle this research with different approaches: magnetotransport in the case of Mar García Hernández, local probe microscopy in the case of Carmen Munuera, mesoscopic measurements like Ricardo Frisenda, and in my case, I work on optoelectronic devices, basically. This is basically how the group looks like now, and I have to acknowledge all these guys for the hard work of setting up all the labs, and now our labs are mostly up and running. Okay, so let's go to the topic, and I would like to start first just talking about two-dimensional materials to give a little bit introduction of what we're going to talk about this workshop. And by two-dimensional materials, sometimes we refer actually to, let's say, more general family of materials, van der Waals layered materials, that they are basically very diverse materials. So you can have in this family graphite, molybdenite, talc, mica, so materials with very different electrical and optical properties, but all of them, they have this appearance of flakes. Okay, so basically, I don't know if you can see in the so this is a molybdenite crystal, right? So in all these materials, they have this layer structure. And basically, you have these strongly bond atoms in plane and weakly interacting layers. These layers, they interact by van der Waals forces. That's why they are called van der Waals materials. And then you can easily separate layers just by cleaving with the Scotch tape, right? So you can see. Oh, sorry. Right, and one can even exfoliate these crystals by just using another tape in order to thin down the crystals that we have. You can see here. Right, so basically, with this very simple way, one can even isolate single layers of this family of van der Waals materials, and therefore one can use these atomically thin materials in order to fabricate devices and so on, just by using this mechanical exfoliation method. Of course, there are other synthesis methods. Some of them they provide large scale materials, so you can even synthesize directly on wafer scale and so on. But still nowadays, this mechanical exfoliation method is one of the most used isolation methods to fabricate two-dimensional materials. Okay? And now let's discuss a little bit about like why we want to study two-dimensional materials. And I work on devices, so I always find easily to motivate my talks based on applications. And if we think about like electronic integration and scaling down of transistors, okay, so we come up to Moore's law, and that basically tells us that microelectronic industry is putting more and more and more transistors every year. You know, and these transistors, they have to be smaller and smaller and smaller in order to keep the prices down, okay, because they want to put more transistors in the same chip, you know, to make more profit. So we are reaching this point here where we are starting to have some problems on the scalability, and this is where two-dimensional materials can start to play a role. Okay, there are different approaches to overcome these problems of the Moore's law. The first approach is what is called Moore. Okay, so it's basically the approach called beyond CMOS, and it's just using the same kind of approaches semiconductor industry has been doing with silicon, but with other materials. And then the idea is to substitute the semiconductor channel that we have nowadays by a two-dimensional semiconductor. Because basically, when you start doing your transistors shorter and shorter, you start having what is called short channel issues. Okay, so basically, when you start having these short channel issues, your semiconductor channel cannot be completely switched off with an electrostatic gate. Okay, but you can overcome this problem by making the semiconductor channel thinner, because basically you start having these short channel issues when the length of the channel is shorter than a threshold length, and this threshold length is proportional to the square root of the channel thickness. Okay, so the thinner your semiconductor channel, the shorter you can make it without having any problems. So that's why semiconductor industry is interested on two-dimensional semiconducting materials, so these van der Waals materials. But also you have a different approach. So you can reach this limit of the scalability, and you can think of what is called more than Moore. Okay, and more than Moore says, okay, forget about making our transistors smaller and smaller. Let's try to make them smarter. Okay, so instead of just being a switch, an electronic switch that makes on and off, so we can maybe think of a transistor in where we have more functionality. Okay, so we just do this on-off stuff and something else. So let's call it photo detection, gas sensing, or even using other degrees of freedom in order to make more logics. Okay, so and there is where all these, you know, spintronics, nanophotonics, bodytronics, all these tronics comes to play a role. Okay, so you take a different degree of freedom and you exploit it in order to make new electronic devices. And that's where this interest on my group on synchronics come from. So basically, we're interested on fabricating devices with a new functionality that is driven by a user-defined mechanical deformation. Okay, so now let's talk about the synchronics. And as I said, this is a field of research in where we want to exploit strain engineering techniques in order to fabricate devices with new functionalities. Okay, so in my group that we are interested on optoelectronics, so the idea that we have in mind is to fabricate a photodetector in where we can modify the output characteristics just by a mechanical deformation that we apply at will. So you can see here an artist impression of what we want to do, right? So we want to apply a mechanical deformation to the lattice, and we want to use that mechanical deformation to tune the output characteristics of our photodetectors. Okay, so and let's see how we can do this. So the first thing is why to use two-dimensional materials in this field of synchronics is because they're quite flexible. Let's say in terms of the way we can apply strain. Strain engineering usually has been used in semiconductor industry and material science by just forcing epitaxial growth of material with different lattice parameters. So in this example here, we have 3 different materials with 3 different lattice parameters. And if we force them to grow epitaxially on top of each other, we end up having compressive strain on this layer, tensile strain on this layer, but this strain cannot be tuned. And it cannot be tuned, then it's not useful for synchronics because we want to use this strain as a tuning node. Okay, so we are not interested in these kind of approaches. On the other hand, on two-dimensional materials, you can apply strain at will. So you can think of two-dimensional materials almost like a sheet of rubber. You can pierce it, you can fold it, you can wrinkle, you can apply strain in many different ways. And moreover, you can change the strain in time. Okay, so this is very unique feature if you compare with three-dimensional semiconducting materials. And these materials, these two-dimensional materials, they can stand very large deformation before rupture. So like close to the fundamental limit of the atomic bonds. Okay, so this is quite unique. And basically combining these things makes unique features of two-dimensional materials. And maybe then these synchronics is a niche application to two-dimensional materials. So that's why I got interested in applying two-dimensional materials to this field. Okay, but so far, even though people are interested on this field, most of the works are just fundamental, and most of them, they work with quasi-static strain. So basically, you apply a certain strain, and you use some kind of optical probe in order to test the changes in the optical and band structure of the material. So like, for example, photoluminescence or microreflectance. There were not that many works dealing with devices in where strain changes the output of the devices. I can highlight one of the first ones from Andrés group in where they fabricated a suspended bridge of molybdenum disulfide, and using the tip of an AFM, they were able of changing the resistance of the channel. Okay, so basically they were doing indentations in this freely suspended layer with the tip of an AFM, and they were changing the resistance of it. So this is due to the fact that they are changing the band structure of the material. So they are closing the band gap when you apply tension deformation. Okay, but from our point of view, this is not very useful for us because it's difficult to implement this kind of approach in an optoelectronic device. So you want a photodetector in where you apply a tension to change the output characteristics. And if you need an AFM tip on top of the device, it's going to complicate your life dramatically. And the tip of the AFM is going to shade the light, it's going to be a mess. Okay, so we are not interested on this approach. Another approach has been reported by Sonnenberger's group, where they were basically exploiting all the technology and all the expertise they have in their group in mechanically controllable break junctions in order to fabricate strain tunable graphene devices. Okay, and this approach is very promising, but so far they've been focusing on very fundamental magnetotransfer measurements, so not really adding a functionality to a device upon straining. And then we have also Stanford's group in where they're trying to integrate two-dimensional materials to MEMS devices, microelectromechanical system devices. But so far, these approaches are just based on optical testing tools. I mean, they are not fabricating electronic devices so far. I think is their goal, but I think they're not there yet. So within this context, we were wondering what could we add to the field of straintronics. And in my group, we are rather good on finding easy solutions to technical problems that they are complicated. And we thought about a way of applying strain in a dynamic way on a device with a very simple geometry. So basically, our approach is to fabricate our devices on polymer substrates that have a large thermal expansion, and therefore changing the temperature of the substrate just by a little, we are able of expanding this polymer substrate and applying a biaxial strain to our flakes. In this video here, what you see is a polymethylsiloxane sample in where we put some holes on it in order to guide your eye, and we change the temperature by 70 degrees, 80 degrees, something like that. And you can see real time with just an optical microscope. You can see it with your eyes, how it expands. Okay, so this expansion is huge. So you can apply quite large deformations on your flakes just by using this trick. So our idea then, it was to fabricate these strain tunable photodetectors, and the simplest photodetector you can think of is what is called a photoresistor or a photocell. It is basically a semiconductor channel bridging two electrodes, and then upon illumination, you basically change the resistance of the device. That is what you do. If we fabricate this device on a polycarbonate substrate that has a large thermal expansion, then we can use a temperature stage to expand the polycarbonate by heating up the substrate or compressing the polycarbonate by cooling down the substrate. So this is what we did. We transferred single layers of molybdenum disulfide, like this one here, bringing 2 electrodes of gold on a polycarbonate substrate, and we can do this with a deterministic transfer tool. So basically, this technique allows us to transfer flakes of 2-dimensional materials to the position we want. Therefore, we can use a pre-pattern electrode, and then we can transfer a flake just bridging these 2 electrodes. Okay, like in this example here, we have 2 electrodes of gold on silicon oxide substrate, and we are transferring a flake of indium selenide bridging these 2 electrodes. You can see it here. Okay, and this technique allows us to fabricate these very simple photodetector devices with almost no cost. All right, so once we have our devices, we characterize them, and what we do is we measure photocurrent or responsivity of these devices as a function of the illumination wavelength for different temperatures of the substrate. And you can see, so basically by changing the temperature, we can go all the way from plus 0.5% strain all the way to minus 1.5% strain by changing the temperature of the substrate from minus 200 degrees Celsius to 100 degrees Celsius. And our photocurrent spectra has this shape here. Basically, we have 2 peaks, B and A, that corresponds to these direct bandgap transitions of our molybdenum disulfide. So basically, this photocurrent spectra gives us some information already about the band structure change upon strain. And we can see how these peaks, they change with the strain. Okay, so they shift towards the red when we apply tension. So basically, we are closing the band gap when we apply tension, and we are increasing the band gap when we apply compression. Okay, this is already telling us that we are indeed changing the spectral responsivity of our devices upon strain. So this is already one of the things we want to see. But we also see this other feature here. For a photodetector, we are more interested in this tail here, because this tail here tells us the minimum wavelength we can detect, the maximum wavelength we can detect with our photodetector. So this is the so-called cutoff wavelength. And we can change the cutoff wavelength by a lot. So all the way from 670 nanometers to 790 nanometers. So it's huge change in the cutoff wavelength. So we start with a photodetector that is blind to near infrared, and applying tension, we can do it quite sensitive to near infrared. Okay, so this is already quite an outcome. We also see an increase of the photoresponsivity upon strain. So if we start with compressive strain, our devices, they have a small photoresponsivity, and they become more and more and more sensitive as we apply more and more tensile strain. Okay? And importantly, so we can change the temperature of the strain of the states of the temperature states real time. So we can make pulses of temperature, and we can see how the responsivity of our devices indeed follows these pulses that we are applying to the temperature states. If we make a zoom in, we see that the response time of our devices is around 20 seconds because it's the thermalization time of our temperature states. It's not an intrinsic property of our molybdenum disulfide photodetectors. It's a property of the thermal states, which is not bad if we compare with another adaptable photodetector like human eye. It takes 10 minutes to adapt to a change in illumination. So these photodetectors, they can adapt to different illumination conditions in 20 seconds, which is not bad. But we can do better. So far, this is just a proof of concept, but there are some problems. Our photodetectors, they're slow, and right now we have some crosstalk because we have to change the temperature of our devices to change the strain. So we would like to ideally just change the strain without changing the temperature. So we are working on these two approaches in order to make them faster. One thing that we have tried so far is to use a microscopic heater instead of a microscopic temperature states. And you can see here how using the microscopic heater, there are indeed several seconds to thermalize, while the microscopic heater can go way faster, almost instantly. Okay. And also regarding the second issue, this crosstalk between temperature and strain. So now we're working on developing a strategy in order to apply biaxial strains without needing changing the temperature, just using a bending scheme with a cruciform. So we are still working on this because we want this approach to be as fast as the temperature states. And with this, I already finished. So just by summarizing that, I hope that I convince you that strain can be exploited to add new functionalities to electronic devices. Very little has been done so far. So you have seen in the introduction that just, I mean, a handful of works in dealing with devices and strain, and there are many issues that has to be solved. And regarding the fundamental aspects of this research, so far most of the studies dealing with the strain, they are using optical tools in order to test the changes in the band structure of the two-dimensional material. So you apply strain and you use photoluminescence, Raman, or reflectance in order to test what's going on. So there is still a lot of things to do with other tools. So we can think of microarpers, we can think of, even STM, any other technique in order to really get an insight on what's going on when we apply strain on these materials. So to get more information and more quality information. And I have to acknowledge, of course, the funding sources, and thanking you for your attention. Thanks.
Thank you, Andrés. A very, very interesting talk. There are several questions popping up, and we have time to answer them, for you to answer them. The first one that we have is from Sumit. It says, what is the role of plasmons when you apply temperature for strain?
I don't know if I quite...
If you have any role of plasmons in here.
I don't know if I quite understand. I mean, for the photodetectors, we're just illuminating with far field light, and our gold electrodes are separated by a lot, so I wouldn't expect to see any plasmon effect.
Good. Now we have a question from Clivia Sotomayor from ICN2. What is the spatial resolution of the straintronic photodetector device?
Spatial resolution in terms of I mean, the minimum sizes that we can fabricate, or?
That's all this test.
Yeah, I don't. So I mean,
so maybe we can give a.
Yeah, I mean, I want to answer regarding the sizes of the dimensions of the device, and if there is something else to clarify, pop another question. So our devices right now, they have like 10 micron separation between the electrodes. We could do them, let's say, down to 1 micron-ish, but we are using all the time like photolithography and so on. So we don't do, let's say, very small devices. Our devices are rather big.
Yeah, I guess this would be depend on the wavelengths of your detection. All right.
Oh yeah, but as we are detecting in the near infrared, 10 microns is
10 microns.
Much larger than the wavelength of
the
light we are illuminating.
Yeah, that's true. So another question is here. How do you calculate the applied strain? Do you assume that the layers are fully adhered to the substrate?
Yeah, that's a good
From
question.
Roberto Oliva.
Yeah, that's a good question. Yes. I mean, we did some finite element simulations in order to learn a little bit about the strain transfer. The strain transfer is a very complicated problem. So far, it's not solved. And what we know is that we have to use substrates with the largest Young modulus we can in order to transfer the strain properly to the flakes. According to our calculations, we should be transferring between 80 and 95% of the strain, depending on the substrate we use. So what we do is we assume perfect strain transfer, and therefore we are getting a lower bound for the estimation of the gauge factors. Okay, so like we are most likely we are getting bigger gauge factors we are reporting, but we want to be on the safe side, and then we assume that we are transferring all the strain. But we know that we are most likely not transferring all the strain. I mean, we always comment on this on the papers because it's a complicated unsolved issue. Yes.
Okay, there are a few more questions appearing here from Virginia Boyce. When you talk about temperature strain crosstalk, have you been able to evaluate the effect of the temperature alone? How much is it?
Oh yeah, I do have a slide here. So wait a second. This. So indeed, I mean, the best thing we can do is we can fabricate devices on, so the very same geometry device on 2 different substrates. One substrate is our polycarbonate that has large thermal expansion, or the substrate is silicon oxide that has negligible thermal expansion in comparison with polycarbonate. And then we subject these 2 sets of devices to the same temperature cycling, and therefore we can try to disentangle these 2 effects. Okay, so this is what we do, but it's not perfect. But what we have done is this, and we can see that indeed this enhancement of the photocurrent is due to the biaxial strain, so it's not due to the temperature, because on the silicon oxide we don't see it. And the shift of the excitons is much more pronounced on the polycarbonate than on the silicon oxide. But there is still one component of the temperature on this shift. So there is a small shift. So we have to discount this effect on these measurements here. So this is what we do to try to separate these 2 effects. Okay,
perfect. I have another question from Felix Boyle. Are monolayers needed because of a band gap change, like tungsten disulfide or molybdenum disulfide, for example, for the 2D material? And how do you ensure that your flakes are only monolayers?
Okay, so we prefer, there is no need to have monolayers for these photodetectors. So we prefer to start with monolayers to avoid one fundamental question, that is Poisson's effect. Okay, so when you stretch the material biaxially, so in the thickness, the material is going to compress. If you have a multi-layer, it is not clear to us what is the effect of this Poisson effect in the photodetector. So therefore, we decided to go to the single layer that is the simplest, let's say, material you can work with, because you stretch it and you stretch it, nothing else happens to it. On a multi-layer, you're going to have a change in the interatomic distances because of this biaxial strain. Say that, so what we do is we select the flakes by measuring Raman, photoluminescence, and microreflectance. So basically, with these 3 techniques complementary, we can know 100% sure that we have a single layer or multi-layer and therefore we select single layers to these photodetectors. But photodetectors can be fabricated with multi-layers and so on. And they work similarly, but indeed one have to start thinking of what is due to the Poisson effect, what is due to the biaxial strain.
I have an additional question from Eugenio Coronado. In these devices, is the interaction between the 2D material and the substrate always van der Waals?
In our devices, it is. It would be better, most likely, to try to clamp the two-dimensional materials by some kind of covalent chemistry. But so far we have not found a way to clamp our flakes in a better way. If we will manage to do that, one will be able of applying larger strains, because nowadays our limiting factor is slippage. So if we go far in strain, the flakes tend to slip. So the van der Waals forces is not strong enough to clamp the materials to the substrate.
I think we are run on questions and also time. Thank you, Andrés.
Thank you.
Very, very, very nice. So our next speaker is ICREAR Professor Stefan